So, what was your general impression about the first exam? Brian? Was okay. Conceptually was okay, right? Okay. In terms of answering each question, so let's go over and see whether you guys understood or if you had any questions in each of these questions. I mean, if you had anything that was not clear to you guys, or was it difficult for you guys to understand or answer. In terms of the topics we covered in the class, that was okay for you because we've tried to stick to examine you mostly from the topics that were covered in fairly good amount of detail within the class. If not, and also your homework problems were also in the same direction basically. So the first question is just asking you to rewrite your block equation. Basically first it was just asking for the frequency in the presence of gradients, what the precession frequency is, and then the second one is asking about the block equations, which is basically mu is d mu by dt is mu cross b. So that's exactly what you had to do, and the whole point was to replace b with b plus gx times x and then gy times y. That was the whole point. So the point to realize was that it's the bz field is what you're always modifying. You don't have bx and by. You always have bz, and you're adding gradients. You're modifying that as a function of x or y dimension. That's the whole point of testing this question. So if I recall correctly, most of you guys got the block equations, everything right, but some of you didn't realize that it was gx times x. People wrote bx, which is not right. We don't have a bx component, and some people just failed to realize that this was the case. So I guess that will help you to kind of realize that now, at least if people who missed that. And the subsequent components are also just testing the same thing. This is just talking about what is the in the presence of B1 field in the rotating reference frame. Basically, what is your block equation? So in the rotating reference frame, again, I remember one of you asked this question: what was how the exam is going to be? And then at one point I mentioned that it is going to test your understanding of your concepts, and you are supposed to remember some of the key equations. You're not going to get any the exam equation sheet, because the whole point of this is to, if you understand the concept, recalling the equations is not difficult at all. So basically the equation that you're going to use here is that b naught minus x prime or y prime, whatever that, in the rotating reference frame along whichever axis you have. So that's your B effective in the rotating reference frame. You derived that in chapter 3 or 4, I think, right? So that's what this is testing. So all you had to do, some people again made this mistake that they added the components here along x, y prime components, but that's not the case, because you're not adding, by adding gradients, you're just modifying this term and not the other terms, right? So that's again the whole point was to realize that B naught is being modified with a gradient. That's all. This one was straightforward. How much phase you would get for at a given point x in the rotating reference frame, how much phase you would accumulate. So basically you're sitting on the rotating reference frame, so the B naught is gone. All you have is the gradient field, and whatever the gradient field is being experienced at the particular x and y location is given by gxx times gyy. So your phase is basically gamma bt or delta bt in this case, right? Yeah. And this one was purely evaluating how well you can realize that it's a 2D square box. I mean, two-dimensional object. You had done this derivation of the Fourier transform of this. Now all it was asking you was to do this along the x and y directions. So this was A and then this was A. So consider the scenario where gradients are applied and your object is defined between minus a by 2 to a by 2 along x and y axis. And what is the signal going to be is basically is the Fourier transformation of this in the presence of the gradients. So is that well, okay, but the whole point of going through this is to kind of make you realize and make it clear to you guys if things were not apparent the first time. So this one is just to is asking you, okay, what is the flip angle, how much duration of your RF pulse, what duration should you apply your RF pulse to get a 180 degree pulse if you the constant B1 field and it's on resonance condition. So it's basically your flip angle is gamma B1 . Again, this is again in chapter 3 or 4, right? So all of that stems from the phase. Actually, so in this case it's the precession about the B1 field, so that's why you have B1 here and it's causing the tipping, so that's why you call that as theta, flip angle, and that's the duration of your RF pulse. So linearly polarized and circularly polarized, again this was in, well, this was discussed in the class, right? Dr. Norman discussed this clearly. So basically all you have is okay, so why didn't somebody, let me, I remember some of you got this wrong. I'm looking at you, and I think you also got that. No, you were okay? You got that wrong, or no? Okay, I should have the sheet in front of me, but okay, so why didn't you got that wrong for sure? So can you explain me what it is now?
There's different, so the external field is B naught C, and B1 is applied.
Right, that's the RF field, yeah.
Right.
Okay, so essentially what you need for the tipping of the RF pulse is a field which is rotating at omega naught, correct? So you can have this field by in physical sense by having a component of the field oscillating here along at omega naught. Okay, so you can write this as summation of clockwise and counterclockwise rotating vectors, and you will end up with a field which is oscillating at omega naught, so sine omega naught, basically sine omega naught t B1. Or you can have two coils which are applying field along this direction, oscillating at, one is oscillating at sine omega naught t, and then the other one is at so this is along x, let's say, and this is along y. So that causes a rotating vector. If you work out the problem, I think one of the problems in the textbook happens that the amplitude that you need to get the this kind of oscillation vector and tipping of for a given flip angle theta, your effective B1 field here is half of the amount of B1 field power you need to the amplitude of the B1 field that you need to apply if you just applied an oscillating field along one axis, which is linearly polarized, versus the circularly polarized where you have two oscillating components. And so basically the amplitude of the applied B1 field is half in the circularly polarized coil versus a linearly polarized coil. So that's essentially what the difference is talking about. So that's what the expected answer was, and it was a simple concept, which is why, again, I guess the number of points for a question doesn't really say it's unimportant concept or important concept. It just is to tally the marks to 100. Let's go to the next question. So this one is okay. So did anybody did you guys draw the RF pulse structure and then figure out what the recovery of magnetization was? This is what it's asking right here. So you have 90, and then followed which basically after the 90 degrees, what is the evolution of Z, and then what is the evolution of M perpendicular? We went through this in the class at least a couple of times, right? And one of the students also came up and then it was you. Okay, yeah. So that's essentially all the difference in this question was that, well, at the end of the next 90 degree pulse, M perpendicular is not going to 0. So what is going to happen to that? That was the question that was the point of this question basically. So if that doesn't go to 0, what does the equation turn out to be? So this was essentially testing your understanding of how the magnetization is evolving, or again it boils down to your understanding of your block equation, signal recovery and decay curves once after your RF excitation pulse. So can everybody derive this now? Can everybody write down these equations? You think? Can everybody confidently say yes? I think most of, if they realized it, if I remember correctly, if you guys realized it, then you started deriving it properly. But even common mistake, and I see, at least in one of the papers, I see some mistakes, is that difference. The general equation is, so mzt is mz at time equal to 0 Okay, so the common mistake is they don't remember whether it's T1 or T2. Well, that's easy. I mean, you shouldn't be making a mistake there. And then M perpendicular is basically M perpendicular at T equal to 0 times e power minus T by T2 or T2 star. Whether it's gradient echo or spin echo, that determines your, if you have 180 degree pulse. In this case, it is T2 star. Now the common mistakes people did was, okay, what is the time axis you're using? Meaning that for this goes till TR. The echo is being acquired, and in fact, in this case, so in this case, actually, this was not the mistake. Yes, people failed to substitute TR for T, some of the students, and some of the students misplaced these. which actually in my view is not a pardonable mistake, because one is talking about longitudinal, the other one is talking about transverse. So there is no confusion of substituting T2 for T1 and T1 for T2. Am I right? Okay, so well, subsequently, at least in the final exam, that would not be an overlooked mistake, I can say for sure, because this is your basic signal equation, or the magnetization equation that you will depend upon in your subsequent course anyway. So just realizing that and then working out at what time what is happening was the whole point of that question. Now this was a giveaway. The whole point of this 20 questions was for you guys who at least did not remember the equations, the basic understanding of simple concepts, you would be able to at least score the points. And I believe most of you did well in this. So the first one is just asking about T2. Some people messed up with the made a mistake in the addition or subtraction between 1 by T2. So so just so if that's not clear, so this is going to be always shorter than these. Of all these three, typically this is the shortest. Just so you guys have an idea. Oh, sorry, I guess yeah. So how do you obtain complex signal? I got a spectrum of answers on this. So does anybody realize now what the expected answer was? Right. Demodulating the signal. I mean, we went through that, right? That's so you use the sine component and then the cos component to get the real and imaginary parts of it. So you get the complex signal. Yeah. Okay. And I think part C was also partly asked in this paper, this second exam also. So everybody remembers what equation that part C was asking about? Right. So the whole point, I mean, one of the key points of chapter between, I think it's 4 or 6, I'm not sure, the one before the 7th, is that the number of protons available to give you the signal is inversely proportional to your temperature, right? So that was the point this was testing. So, and if you come to chapter 15, you could probably answer another part of it. Remember the in chapter 15 we went through that the bandwidth, the effective resistance of the coil also reduces as a function of temperature. It was 4 kT by 4 kT bandwidth. Yeah. So it's square root under square root 4 kT bandwidth, right? So that's temperature. So that it's inversely proportional to that. So that will also become a part of it. Now you have two dependencies, one on the coil side, one on the sample side. Okay, data truncation. So part D, does everybody know the answer to that now? Right? Everybody understands that? So there are two effects, right? One is the finite sampling effect, and then the other one is data truncation effect. So data truncation causes skip ringing. Finite sampling, if you so finite sampling is the one that is leading to your aliasing problem, right? Okay, so and part E, can you guys read So what, everybody knows the answer to the party? We looked at this animation also, right? When we were filling up the case space. Right, high frequency. So until you fill the center part of the case space, the bulk part of the image is not clear, but you can see the edges. Whereas the converse is true. Once you start filling the center part of the case space, you can at least see the brain partly, and then the edges become finer and finer as you go to higher and higher case space. So that should be very clear to you guys from that animation as well. Okay, so everybody now knows what Nyquist condition is. Okay. Okay, part G. Does anybody have a problem with that now? I mean, still. Everybody knows the answer to that. You're okay. I mean, everybody said yes, but you understood part G. Yeah. You're good. Okay. Okay. Part H. What is it asking about? The inversion recovery. Okay. So this one was just testing you. Well, you could have derived this also. Even if you forgot that equation, T1 ln 2, you would have derived this very easily. All we were asking was where is the zero crossing point for that m naught into 1 minus e power minus t by t1. Correct? So, and part I, okay, that is granted, that's a bit tricky. We went through the filtering part of case space. Right, in this case, this is symmetric. So the whole point this was asking was, okay, what is the filter shape and what is its effect? Even if you couldn't answer the filter shape, actually there was a homework problem on this, and you guys, that was one of the homework problems. Just deriving, this was more or less a giveaway in the homework problems, right? So if you did homework, then you would have gotten this very easily. And what is its effect? That we went through in the class. What happens when you have a decay riding over when you're sampling your case space? The full width half maximum of your filter, the point spread function. Yes. So when you have something overriding your case space, when it's modulating your case space other than your imaging procedure, which is basically your gradients, then some sort of blurring is going to occur. Basically, it's going to modify your point spread function. So it will lead to spreading of your signal coming from a location X, leaking into the surrounding region. So how much of and what's the shape of that point spread function depends on your filter function. Again, this was a giveaway. Okay, so most of the people lost points where they were not showing, okay, what is your gradient step in terms of the labeling. Basically, most of you got that right. Some people forgot to apply a 180 degree pulse, and that is not pardonable. It says spin echo. So if you forgot the 180 degree pulse, then that's a problem. And actually there was a variant people used, some people used for the so you could have two variants, right? One is the refocusing one here, and then your 180 degrees can also be slice selective. So some people we didn't say this is multi-slice, but I believe I gave points for either case, but typically it has to be slice selective, because this is well, if you're doing 3D, Yeah, actually it helps to have this as slice selective, but it can also be non-selective. So I believe I give points either way. When you used it or when you didn't use it, I gave points for either case. So yeah, most of the students lost points when they didn't have the right labels, the duration. The whole point was to realize this part and the phase encoding part, and then in this case your phase encoding can be here or phase encoding can be here, either way, and your dephase and rephase gradients, the areas, all of those, and your yeah, of course, right. This is 3D, right? Yeah. So you have partition encoding also. You can have that here, and you can have that here also, either way. So those were the variations, and the points were mainly for the durations and then the change between these, meaning showing the gradient step. What is the equation for that? What is the duration of your gradients, readout gradients especially. So those were the important points in that. So this was a fairly straightforward question. If you reduce your field of view, if your object is smaller than your field of view or larger than field of view, what happens? And then how can you change your keeping the voxel size constant, how can you change your field of view? What parameters you can change to, and you basically had to use your Nyquist equation to see what parameters you can change to realize that. And in which scenario would your TS change? Basically, this is what the part C is asking. In which scenario will your TS change? Transverse relaxation effects has everything to do with your TS. This is going back to your part G question in your going back to this question, basically part I, sorry. So if you have T2 decay or T2 star decay during your sampling, and you are changing your sampling duration, increasing or decreasing, basically with respect to your T2 star, which is more desirable? If you reduce your T2 star, TS, sampling duration, so your effective filtering duration is shorter of your K-space, right? Now, if you're reducing it, your bandwidth is changing, your noise is going to change, that's a different story. We didn't go to that part yet. Now you realize that it's not such a simple change, correct? If you change your gradient, okay, I guess so here you can change both G and delta T. Okay, so if you change delta T, then your TS is going to change. If you change your G, your bandwidth is going to change. So which of them is desirable, keeping the relaxation effects in mind? If you're reducing your delta T, or if you're increasing your delta T, then you have more decay influencing your signal. So that's what I wanted you to kind of point out. Whereas if you change your G, of course your bandwidth is going to change, it will increase your noise. That's a different story. We didn't come to that yet. Now you realize that that's what is going to happen. But that was not what was being tested. And this question was also, so how many of you still don't know how to answer this? That's just giving you the basic information. These are the questions. So basically, that's what I wanted you to draw. And realizing that that's 45 degrees, that was also an important point because your gradients were equal. So the angle that it would make at within the K space is is that 45 degrees, and then how can you change that to 30 degrees? I mean, if you were able to answer this one properly, then the answer to that one was already buried in part B. It was already obviously there in part A, because if this was 45 degrees, by changing your k gradients along along the y direction, basically, you can change your so your gy is going to change. Well, rather in this case gx. See, one of them was constant, right? So both of them were equal to g. So that becomes important in this case. If you express everything in terms of g, so part C was, what is the value of ky max expressed in Ts and g? Now ky max is what the coordinate along the y-axis. What is the maximum coordinate value? What is Ts here? Everybody know that? That's your sampling duration, right? So I guess so this goes to any exam. If it's not clear, because some of the context is already understood that the student understands, we don't have to, it would be good to explain each of those terms, but then the question paper will be 10 pages long, and by the time you read your question, you will probably be half the way through the exam, which is not going to be a good thing. So we are assuming that from the context from the course that you know what each term means, because throughout the class we are not changing the labels, right? We're keeping the same labels. Ts is sampling time, and gx is your x gradient, gy is your y gradient, gz is your slice select gradient. So those haven't changed throughout the course. So this was just testing your understanding of traversal of k-space. First one is just is showing, okay, is asking you how you cover the k-space for such a gradient structure. So you're applying a d-phase gradient in both x and y directions. So along the x you go, if this is your k space, along the x you're going this way, and then you're also simultaneously applying the y direction. So you're basically traversing something like that, and then how much you're going for a unit distance is going to determine what angle you're traversing. So because the amplitude of each of those gradients is equal, so it's basically 45 degrees. So the d phase part is taking you this side, and then the re-phase part is just traversing back, which is that. And then to change that angle to 30 degrees, or this one, so you're changing that angle to 30 degrees. So you're changing your amplitude of your gy gradient. So earlier gx was equal to gy, now it's square root 3 gy. What is square root 3? It's 1.7. So that means that it's greater than the previous amplitude. And in the second part, part C, you're just asking what is the ky max. So that's basically, so what is the definition of k? What's the definition of k, anybody? It's integral of, right? So because it's constant, so you're ending up with gamma bar g t. Now the total duration you're traversing k-space is Ts. In your so that is your Ts. during the D phase part, which is this, you are here, and then you're sampling the k-space from there on the full line, which is your TS, right? So ky max so you're taking total time t to traverse from minus ky max to plus ky max. So ky max is basically gamma bar g ts divided by 2. Is that clear to everybody? Yeah. Okay, so that brings us to the end of the first exam. So, and these are the concepts that we all of us, I mean, we discussed this in the class, all of these questions more or less. So if you still have questions in it, you can always ask Yungchan or email me, that's fine. But the point of having this review was to see if you still had any specific questions, or if things were not clear to you guys at any point in the exam, or in the questions, I mean the concepts that were questioned in the exam. So I think Yungchan is going to review the second exam now and then see if you still have any questions. Yeah. Okay, thanks. Yeah, you can close that, I guess.
Is it working now? Okay. So a quick question after reviewing the first exam, and so which one do you think is a little bit more difficult? The exam 1 or the exam 2? Two?
Absolutely.
Oh, really? Okay. But statistics doesn't lie. Actually, we have 10 students attending this, both exams. So 7 of them having almost the same scores for both exams. So I think they are pretty, close. Okay.
You mean 7 students got good marks?
7 out of 10 have almost the same scores between the 2 exams. So it's not it does not mean that exam 2 is significantly, more difficult than the first one. So as I said in the first class, that the second part of the book of this class is actually more application oriented. So it does not we are not giving you as many basic principles as in the first part. So so it's basically it's the same idea of this the second this midterm exam, that most of these questions they are actually based on practical applications. So you will encounter this if you really need to do an actual scan and do something. So this is basically just solving the practical problems. Okay, so let's first take a look at the first the first question. So the first question, we have 5 sub-questions. So here, the first question, we have a very high accuracy rate, and then the scoring rate goes down. So question 1A should be pretty easy if we do 3D imaging, right? So for each TR, we acquire one k-space encoding line. right, in the 2D or 3D K-space. So the total number of K-space lines we need to acquire is ny multiplied by nz. So the total time should be ny, nz, and multiplied by tr. So that should be the easy question. So the second one is about the if we have a 5 echo alternating readout instead. So this is like a multi-echo acquisition. So this is when we are collecting 5 echoes in a single TR. So each TR we collect like 5 phase encoding lines. So the total time would be just like 5 times smaller than the first one. So it's just the first one divided by 5. Okay, so and then question C is to draw out the K-space filling schemes of 2 segmented K-space schemes. So the first one is the simple offset, and then the other one is the interleave. So I was surprised to see that most of you get confused between these two. So most of you draw the offset under the interleave segmentation and the other way around. So the offset is, so why do we call it the offset? Is that each segment of the K-space is, each segment of the K-space, they occupy one part of the K-space, and which can be just simply offset, shifted to, create a whole K-space. So this is the simple offset. So each one offset. So each one was collected with the same with 1 TR. So with the K-space lines that's collected by within 1 TR. So in this case, we collect 5 K-space lines. So let's say this is 1, then 2, because we said it's alternating readout. So 3, 4. Let's say this is 5. So 1, 2, 3, 4, 5. So the ascending scheme would be to collect the first TR, and then the second TR, third, go on. So in this from bottom up. So this is the ascending scheme of filling the offset. Simple offset segmentation. And for the interleave, is that we have we also have different segments of the K-space, but the K-space line collected in each TR was used to fill in the K-space lines in different segments. So that's what's called interleave. Right, so this is the direction. So this is the first echo, second, third, 5. And then the next one filled in again, right? In the same way, just shifted a little bit. So this is the interleave. So so each one would have 4 points. The correct labeling of these directions of the echoes, the K-space filling line directions is 1 point. The correction of this label is another 1 point. Showing this ascending scheme in here is also another point, and also the rest of this K-space is another point. Okay, so is there any questions about this? Okay, so let me see. So what is the gradient moment? The fourth question, 1D. What is the gradient moment of the phase encoding blips needed in terms of delta ky? So it means we can use delta ky to represent the final answer. So in the simple offset, so each one, right, each blip, we shifted one k-space line. So actually this one is just delta ky here. And in here, we shifted how many lines here? We have shifted so many lines. So in here, so each, because 5 echoes was used to fill in 5 segments. So that means the k-space has 5 segments in this interleaf. In this interleaf scheme. So each segment contains ny, just 1/5 of the total case encoding lines. So that means each shift in here is 1/5 of the total case encoding lines. So that means this the blip, the phase encoding blip in here, they are this much. Oh, can you see it? So it's right, because you need this ny/5 k-space line shift to fill in this interleaf. Okay, so also yep. Oh, yeah, and also in here, there will be like 5 segments in the interleaf scheme, and there will be ny/5 segments in this offset, right? Because each segment only contains 5 k-space lines. So this one is also 1 point here.
What does that gradient movement mean exactly?
Actually, it means how much k-space, how many delta ky it can give you, right? So the phase encoding gradients, right? So its function is to shift you along the ky direction, right? So the amount of this shift is can be used. So as we use the delta ky to represent it, so it's pretty easy in here actually.
So for the opposite scenario, we just need to write down delta ky, right?
Yes, just delta ky.
We don't know.
Yeah, we don't know, because I said in 1D we just say you can represent it in terms of delta ky. Okay, so 1E. So 1E is a little bit, it's not related to the segmentation, but just multi-echo, gradient echo. So we have excitation, and then we collect multiple right. So I said it is single shot gradient echo EPI, right? So this is a single shot gradient echo. So that means we are collecting the FID signal after the excitation. So when we have excited the signal, then the signal would decay according to T2 star, right? So the idea of this question is just to ask you how long it will take for you to get a useful signal before the T2 start decay the signal to the noise level. So we also want to test the concept between the bandwidth and readout duration in here. So when we say the signal decays to noise level at 3 T2 star, so that means we have like 3 T2 star as the total time. So the question is, how many readout can we put in for this in this duration? So for how many echoes here, then we need to calculate the duration of each readout. So since we know the bandwidth, we know the readout number, so we know the bandwidth. So let's say each readout so we have delta t equals 1 over bandwidth, right? So the total duration of one readout is so the total duration of one readout is nx bw, right? So we know the total duration is 3 T2 star. So the number of echo is just like 3 T2 star divided by TS. So star BW and NX. So this is the expression to show how many readouts we can stuff in during this 3 T2 star duration. So put in those values and you can get 75. So the idea of this question is that after 75, if you want to collect more phase encoding steps for the EPI, you really don't gain any extra information because it's only noise now. Okay, so the second question is it's actually some try to give you some points. Okay, so 3 different strategies will reduce the total requisition time of any MRI sequence without affecting the image resolution. So to reduce TR, right? To reduce FOV while reduce sampling number accordingly. That's also the question. We can use the segmented K space or multi-echo acquisition. And if you know more, this is actually basically an open question. So if you know something more, you can say parallel imaging, compressed sensing, anything. So anything that is correct will gain points in here. But as long as it's satisfied the condition here, it does not affect the image resolution. And the second one should be a pretty easy one. So to achieve proton density weighting for gradient echo sequence, so the basic idea is to have a small flip angle, short TE, and long TR. So for those who has written the condition like flip angle far smaller than much smaller than the 2O pi or Ernst angle, and TE much shorter than the T2 star or T2 TR much longer than T1, that will be correct. Okay, 2C is this one is trying to remind you on one of those early chapters where the signal expression is derived from the the signal is derived from the different physical components. So basically, it's trying to have you remember this. Something like this, right? We same thing also showed in the first exam we just saw. Okay. So for those factors that are not sequence related nor the sample related, they are basically you can answer any of those here. So the temperature is one that affects the signal intensity. The B naught can affect the signal intensity. The sensitivity profile of the coil, right? The received coil field sensitivity can also affect it. And also the voxel size can also affect the signal. And the next one is the noise. So another two factors that affects MRI noise. The noise is remember is equals the component from the body plus coil plus electronic. Right. So for this electronic and coil, you can answer temperature, right? Temperature can actually increase the thermal noise, and also physiological noise, receiving coils, and anything. So this is also like a open question, as long as the answer is not sequence related or sample related. Okay. For question 3. Okay, so for the to derive the SSI signal, so it's on the textbook. So I'm not going to list here. So we have if you have already derived the longitudinal magnetization, then it's right. But if you only write that the final result without the derived process, then you'll have some points removed. So the longitudinal is like right 1 minus E1 cosine theta. So this is the longitudinal. But for the second question, so the contrast to noise between two tissues for an SSI gradient. So the contrast to noise. So the definition is CNR is S1 theta. We are assuming the same noise. So that's in here. So for the S1, it will be something like this, sine theta, right? And E2. And for this S2 will be just E1 prime and E2 prime here. So the contrast to noise ratio is then just S2 is equals M0 1 minus E1 prime 1 minus E1 prime cosine theta sine theta E2 prime. So the CNR is just S1 minus S2 divided by omega theta. And okay, so the third question: what is the flip angle when there's no signal contrast between the two tissues? So that means in that case, it's S1 equals S2. Right. So that means this one equals this one, and you do the, just move over, and you can get the result. So it's a little bit difficult. So the question of 1C, the answer of the 1C is C equals 0 is cosine 2. So that's why this is a little bit complicated, but basically it's very easy to come up from just by solving this equal problems. Just
here you assume that rho A equals rho P, right?
Yes.
So, I mean, from where did you make this assumption?
So we can say it's M naught or rho naught here. It's okay. Either way is okay. No, we just consider identical equilibrium magnetization M naught. So.
Well, I didn't realize that I used rho A and rho B and didn't consider that they are equal. So my final answer is not
right, but there is no. Well, actually, if you have the same equilibrium magnetization.
The way that you got this equation, exactly the same way, but the final answer.
Basically. So I gave you those points that you deserve, right?
I did all those calculations, but with the assumption that E1 times E1 prime can be assumed as 0.
Yeah, you cannot. How can you? Well, you cannot assume that.
Because comparing to, for example, E1 and E2 separately, E1 times E1 times E1 prime, I think would.
Right, but still, you have there's no you cannot make that assumption in here because we did not say that it's a longitude or longitude or relative to T1, right? So because it's only symbolic deduction in here, so this just even if you want to make that assumption, you need to at least come up with this one and then make
because I came up with a similar equation, but
right. But I remember you did the assumption in the middle of the calculation.
Yeah.
Right.
No, it's not in the middle. It's very.
Okay, so I'll look at it after that. Okay. Okay, so question 3D. Then when we say T1 equals T1 prime, then we have E1 equals E1 prime. So we just use E1 to replace the E1 prime here, and we can get the result And just simply we can get the result of cosine 1 over E1. So this one in here, it means that the flip angle, this non-contrast, this zero contrast flip angle is only determined by the T1, and it has nothing to do with the T2. And when the T2 equals T2 prime, and then we just use either T1 or T2. Use the E2 to replace the E2 prime, and we can come up with this one equals 1. So that means this theta is now cosine minus 1. So it can be 2n pi. Right. So that means that as if the T2 is equals to T2 prime, we have then that means the image contrast will never be 0 as long as T1 is different. Because practically this one is 0, right? For the n equals 0. So that means we need to use a 0 flip angle to achieve 0 contrast. So that means practically you cannot achieve 0 contrast with any other flip angle. So that means the idea of this question is that this special 0 contrast flip angle is only T1 dependent, right? Okay, so question 4. Question 4a. So question 4a asks us to use the definition of the gradient definition of K-space and the relations between the K-space and FOV to deduce that scaling factor caused by the background gradient. So the definition of the K-space, right? The definition K is gamma bar G T. So we have set in here in this case is gamma, let's say GX, right? T. So this is the definition. So when we use the delta K is GX delta T, right? So this is the definition of it. And this, the relation between the K-space and FOV is, of course, 1 over FOV X. We use LX in here, right? Either way, we do not say it. Okay, so when there is background gradient, is the FOV X prime. Okay, so the lambda is defined as FOV X prime divided by FOV X equals GX X prime. Right. So that we use the definition of the K-space, the gradient definition of K-space, and the relationship of the K-space between the K-space and the FOV to deduct this scaling factor. Okay, so the two possible effects that the background gradients may cause is like we have talked about this before, right? So it includes like the echo shift along the readout, rotation of the slide selection plane, right? And also, and for the C, another two possible effect of a background gradient GZ may cause is like change the slice thickness and the shift of the slice center or its location.
Can you say it again?
Which one? C. Change of the slice thickness and a change of the slice center location. And also, it can also cause signal deduction, because due to the echo shift along the, Z direction. Okay, so any question about question 4? All right, so let's go on to the question 5. Okay, so 5A is very simple. Most of you got it right. So it's just like the, just the gamma R multiplied by the chemical shift and the B naught. So you can get the result of 2.793 Hertz. Right? Okay, so the chemical shift along the readout and phase encoding in gradient echo EPI sequence. So basically we have this delta omega between the water and fat. So what we need to do is calculate the bandwidth for each voxels along the readout direction and phase encoding direction. So the bandwidth of the readout direction for each voxel is simple. So it's just like 512 kHz divided by nx, right? So the shift along the readout is this delta omega water fat divided by this one. So the shift in readout delta x is 0.21 mm. So if this is so this one is I don't know. So it's just basically the delta omega, right, divided by this one. So Hertz by nx. Okay, so for delta y, for the so for the bandwidth along the phase encoding direction, as we have talked about this before, right? So the k-space filling path of the single shot EPI is like this, right? So this is the center of the echoes, right? Because it's the center of the readout. So the delta t y between these two echo center. How long is that? Huh?
The time of readout.
Yes, the time of readout, because it's half the readout here and then half the readout here. So that means it's nx. It's time of readout, so which is the ns delta t. Right. So the bandwidth along the y direction is 1 over delta ty, right? And so we have the my, we know the my, so the bandwidth per pixel is bandwidth y divided by my. So that means it's, can you see it? So it's divide this one in here. So it's the n x delta t, and then divided by n y. Is it? This one here. Oh, okay, sorry. Bandwidth per pixel is 1 and x delta t and ny. Right. So the bandwidth for each voxel along the k space is this one. So the delta y in here is now the delta omega water fat divided by this one. So it's like multiplied by nx. Delta t is bandwidth x and ny. So this one is now 54.8 millimeter. So we actually talk about this in the review. So is there any questions about this? Got it? Yeah.
I got a question here. I wrote that bandwidth for bandwidth y equals bandwidth x over nx. Is that right?
Bandwidth y, the total bandwidth.
X over nx. Because bandwidth y is 1 over tx. The t readout. So it equals 1 over nx delta.
Which one?
Delta dx. The second line.
This one?
Yes.
Okay.
So delta t.
What did you write?
Can I?
Yeah, sure.
So I wrote bandwidth y equals 1 over. Is that right?
Nx delta t, yeah.
It's t readout.
That's right.
So it would be 1 over delta t would be bandwidth x over nx.
That's right.
And bandwidth x, I calculated here, and I think it would be 2 kilohertz.
No, bandwidth x here is 212 kilohertz.
Bandwidth per voxel.
Yes.
It's 2 kilo. Oh.
Yes.
Yeah. Okay. Sorry.
Okay. Yeah. So on hand, just to further understand this bandwidth, right? So let's say this is the x, right? We have gradient gx around here, right? And let's say the FOV. So this is the FOV along this direction, right? So this total, the total bandwidth. What is the total bandwidth in here? No, the total bandwidth using these two. So the bandwidth equals
Gx times
and gamma bar, right? So the total bandwidth in here. But in the image, right, we have voxels. So this, let's say, so we have the voxel, each one occupies a dimension of Lx divided by Nx. So the bandwidth per voxel, right, is the bandwidth, So this is the bandwidth per voxel. Right. So if we have a shift of frequency of delta x, delta omega. So so how many voxels if there is a shift of delta omega, right? So the delta omega, the shift in the image would be delta omega divided by this bandwidth per pixel divided by bandwidth per pixel. So this is the shift that will be observed if there is a frequency shift of for those voxels, right? Then that means its location would be encoded differently. Okay, so and then 5C, it's a little bit more. 5C we also talk about it, right? Because there is a frequency difference between the water and fat. So for the water and fat, when they were immediately excited, we have phi water equals 0, and let's say phi fat also equals 0. But after a while, and let's say we use the waters as the reference Lambda frequency for the rotating frame, right? So we would not see any phase development, but we will be seeing a phase development. So T. So 5 omega water still is 0, and T equals delta omega T. So there will be a phase difference between those two. So what we are asking here is that after, so there is, when this time, when we have it has a developer time, the water at a specific time, the fat signal would be having a pi phase difference as the water. So in that case, it will have a. So in this case, we will have negative. A reduced signal if the voxel contains both water and fat, and the signal intensity is the sum of both. And then after another time, then the water and fat, the water is still 0, but the fat has processed an extra lap, extra 2 pi, and it now has the same orientation, but a 2 pi different phase than the water. So in this case, then the two signals will add together, right? For those overlapped voxels. So the time that is needed for the fat to process an extra pi would be just like a pi divided by delta omega water fat, right? So So this one here is so data water fat is let's say 428 hertz 2 pi. So this one would be to 1.17 ms. So the same for this one, it will be 2 pi divided by delta omega water fat equals just twice of that time, so it's 2.34 milliseconds. So if we collect the data, use this one as the TE, we can collect the minimum signal because the signal of these two samples cancel each other, right? And if we use the TE of this one here, we'll get a high signal because they add to each other. So that's for question 5C. Right, is this one clear here? Okay, so the next one is the more fun part in here. Now we have now the TE for the minimum TE. When we set the minimum, because as time goes by, it will go through this pi 2 pi 2 pi. So we will see observe oscillating pattern of the signal. So when we say the TE minimum TE, that means we're using the shortest TE when this first cancellation and addition of the signal occurs. So for the C, let's say the lowest signal is 1.17 milliseconds, right? And T, the highest signal is 2.34 milliseconds. Okay. So the question 5D is, we just need you to write down the signal expression of the gradient echo. So the signal of the gradient echo is what is simple. It's just like M naught, right? And actually just E2 star. So this is what we need you to write down in order to solve this question. So so the signal actually now the signal intensity would be now M naught for water, right? For water, okay, sorry. So let's say at this one here, the water signal is M naught because it has magnetization of M naught, so it's M naught here. It's by X. So as long as you have written this and you just put down these values, right? We know the T2 star of the water and fat. We know the signal intensity, right? So for this one, for the minimum, and then we just use this one to put the TE in here, and then we have the signal as the S water minus S fat, right? So S min. So and S maximum would be the S water plus S fat, using the corresponding TE and T2 star. Okay, so is there any questions about the question 5? Okay. Okay, for the final question, number 6. Okay, so 6A is pretty easy. Most of you have, have come up with the right answer. So 6B. 6B is okay. So that's according to this. Let's just draw the sequence diagram. So it's simple. For a gradient echo, right? So it's a gradient echo. So we have the R pulse, we have the slide select, right? We have the phase encoding, and we have the readout. Okay, so we said here the starting time of the readout gradient is 5 milliseconds from the center of the RF pulse. So that means the start up here is 5 milliseconds. And we just said that we told you that we assume the slide select gradient and the reverse the phase encoding and the pre-phase gradient here, they are all included in this 5 milliseconds. So we just say this is the starting time of the readout gradient. Okay, so right, so it should be quite clearly written in the question. So the idea is the idea of this the question 6 is to let you know that how while we change the bandwidth of the readout, how can we compensate? Actually, we can compensate it by using the loss of SNR by using a different TE, right? Because with a higher bandwidth, you potentially get a lower SNR because the noise has increased. But with a higher bandwidth, you get a shorter readout. And then you can push the readout, right, a little bit forward so that you can get a shorter TE, which will gain you back a certain signal intensity, right, that is with less T2 star decay. So the idea is this is the idea for the question 6B. So basically, well, we know the bandwidth, so we just calculate the readout duration under different bandwidth, and then the TE would be half of this readout duration plus this initial 5 milliseconds, and that would be a TE. And then and then use this TE and gradient echo signal intensity expression. You can calculate just simply calculate the ratios between these two conditions. So the TE, the general TE expression is in here is 5 milliseconds plus half of the readout duration. So the readout duration is delta 1 over bandwidth, right, multiplied by nx. So this is the TE. So you use the different bandwidth, and you can calculate the TE1 and TE2. And then the SNR, the definition is SNR is S over the noise, right? So S, for the signal, we have, it's M0, and then we use the same, we use this, let me see. We use the same TR, so it's basically the same question from with question 3. So it's 1 minus E1, 1 minus E1 cosine theta, and then sine theta, E2. Right? We did not say anything about theta, right? We did not say anything about theta in here, but since we will be using the same TR. We are using the same TR here, so the E1 of the two is the same. Cosine theta, the flip angle is the same. So basically, when we are so S1 in here, S2 is almost the same, right? So it's the same sample, so we will cancel this one, right? So SNR 1 minus SNR2 equals S1, S2, and then 2, sorry, step 1. Right, so let's say it this way. So the ratio is like this. So S1, so let's say the ratio between S1 and S2. So we are talking about the same sample. So this one will cancel. We are talking about the same TR and same T1. So this and the same flip angle. So all these terms will cancel. So basically, it's now for the the ratio of the signal is just E2 and E2 prime with different between the different two bandwidth. So the noise in here is proportional to bandwidth, right? So it's bandwidth 1 and bandwidth 2. So just use this to put in there, and you can get the final SNR. So to answer this question, you need to come up with the correct ratio between the noise and the correct ratio between the signal due to the T2 star. So, is there any question about this? Understand this? Right. So yeah, it's and for the 6C, it's basically the same, but now we are also throwing in the E1, the TR. Right. With a shorter readout, you can also have a shorter TR, and basically it's the same. You still need this equation and do the ratio between this between the signals, but now the E1 term is changed, and then we have given you the flip angle here. It's 30 degree. We have given you the T1. So all you need to do is calculate the TR, the shortest TR under the different bandwidth, and put it in here and do the calculate the ratio. So yeah, I think that's it. The next this Thursday is the hands-on section for you to visit the MRI scanner. So we'll send out the instruction for you how to get there. We have reserved the scanner because the scanner schedule is a little bit tight, so we only be able to reserve the scanner starting from 3 p.m. So can you guys all make it to at 3 p.m.? Okay, that's good. So we'll send you the instruction to how to get there, and we start at 3 p.m. So is there any questions regarding this text? Okay. So yeah, if you have further questions, just come and we can discuss. All right. So see you Thursday.